Deep learning has completely turbocharged modern AI. This incredible algorithm that can automatically detect the important features out of data. And from this algorithm, it could construct hierarchically knowledge representations. And these knowledge representations, if you give it enough information, enough data, it would become more and more robust and recognize a larger diversity of that space, become more intelligent. Deep learning has revolutionized modern AI. The thing that deep learning needs, though, is a ton of data, and more importantly, a ton of compute. And the reason for that is it just iteratively goes through and tries to figure out what are the important features using all of these incredibly revolutionary algorithms. Our strategy at Nvidia is to advance GPU computing for deep learning, for AI, at the speed of light. From the processor development to the systems, the interconnects, the way we construct systems, to all of the software layers that are on top of it, making it available and partnering with cloud service providers and OEMs everywhere. Irrespective of what AI framework you use or what AI network you're trying to create, wherever you are, we will support it. And we will support it from end to end, so that the frameworks that you use to develop the networks and models will be deployable in large scale. And we would even make it possible for you to access our platform in every possible way and in any sort of way. Whether you would like to build a personal supercomputer for a few $1,000s with our Titan V, or to be able to rent time in the cloud for a few dollars an hour, or to be able to build your own supercomputing cluster, or just to buy one from us. We're going to make it possible for you to do your work at the speed of light and to be able to do it anywhere. Today, we're announcing several big things. First, we are doubling our GPU. The Volta V100 is now 32 gigabytes of HBM2 memory. It's twice the size of what it used to be. Now, this is so important, and the reason for that, and I'll show you later, the networks are getting larger and larger and larger. And so it doesn't fit in 16 gigabytes. Researchers would like to not worry about memory size while they're developing their neural networks, and 32 gigabytes gives them just a lot more space. HBM2, the fastest memory in the world, connected to the Volta V100. It'll be available as of now, and the next DGX as you buy, it'll be available in the cloud very, very shortly. It is in complete volume production everywhere. The new Volta with 32 gig. Neural networks are growing and evolving at an extraordinary rate, at a lightning rate. What started out just 5 years ago with the AlexNet, Alex Krizhevsky's now world-famous AlexNet, was 8 layers deep, had millions of parameters. 8 layers deep, millions of parameters. 8 layers deep and millions of parameters. It's a CNN. The CNN was first developed and produced or created by Yann LeCun, and the training technique is called stochastic gradient descent by Jeff Hinton. And it was implemented in AlexNet for the very first time, and it won the ImageNet competition. Well, 5 short years later, thousands of species have emerged. Thousands of species of artificial intelligence networks, models of all different types, from the CNNs of Yann LeCun to the RNNs that was first done at Schmidhuber's lab in Switzerland, the generative adversarial networks of Ian Goodfellow, the deep reinforcement learning that was most recently done by DeepMind, Demis's DeepMind, and Peter Beal over at Berkeley. All of these different architectures have hundreds of different implementations. The number of species is growing so incredibly, and there are so many new ones coming out. Hinton just recently disclosed the capsule net so that it could not only recognize images in its image form, but to learn the geometric form of the images. So many new techniques. Neural collaborative filtering, NCF, which is used for recommenders. What started out just 5 years ago as 8 layers and a few million parameters is now hundreds of layers and billions of parameters. 8 layers and hundreds of and millions of parameters to hundreds of layers, billions of parameters. Neural network models have increased in complexity, not to mention the number of species, the thousands of species that are now out there. Neural network models have now grown in complexity 500 times. In just 5 years. 500 times in 5 years. Remember, Moore's Law would have only kept up with 10x of that. 500 times in 5 years. So the world wants, the researchers all over the world wants, just a gigantic GPU. Not a big one. A gigantic one. Not a huge one. A gigantic one. And so, ladies and gentlemen, today, I would like to announce the world's largest GPUs. This is the world's largest GPU. This is 16 Volta equivalents connected by 12 brand new high throughput switches that the world has never seen. It's called MV switch. These 16 Tesla V100 equivalents, each with 32 gigabytes, creates virtually a 512 gigabyte memory. Not only that, these 512 gigabyte memories, the way you address the memory and the way that every single GPU could talk to the memory of another GPU, completely using the same memory model. The memory fabric semantic on our chip that connects all of the processors have been extended out of this chip, out of the GPU, onto the MV switches, connecting each and every one of them. In total, 14 terabytes per second of aggregate bandwidth. 14 terabytes. So that's, what is that? Let's think about that. 14,000 gigabytes. And let's say if a high resolution movie is 10 gigabytes. Okay? So 14,000 gigabytes, 1,440 movies. 1,440 movies. More movies than any human has ever seen could be transferred across this switch in 1 second, like that. Ladies and gentlemen, 14,000 movies. $14,000 movies downloaded in 1 second. Dream come true. Altogether, 81,900 CUDA cores, 2 petaflops. This GPU is 2 petaflops. I told you earlier, the fastest supercomputer on the planet is 125. The fastest supercomputer in America is 100 petaflops. This is 2 petaflops of tensor cores for AI on this GPU. The world's largest GPU. Let me show it to you. No. That thing. Hang on a second. You know, guys, here's the thing. We're so busy pulling this stuff together, we don't rehearse. Okay? Our rehearsal is basically grip it and rip it. Ladies and gentlemen, the world's largest GPU. You didn't fall for that, did you? You didn't fall for that. Hang on a second. This isn't the world's largest GPU. This is the world's largest GPU. Guys, it's sitting in plain sight, hiding in plain sight right here. Sandy, if I could give that to you. Now, I understood earlier that was that the game plan for me to do this myself? Oh, okay, it wasn't? All right. Ladies and gentlemen, grip it and rip it. This, ladies and gentlemen, is the world's largest GPU. Now, what you're looking at is something that's really, truly amazing. So let me show it to you this way, and I'll come back to that. Okay? This switch has 2 billion transistors made of TSMC's 12 nanometer FinFET. This, great process. Every one of these switches, and there are 12 of them, every one of these switches has 18 links, which are 8 bits wide, 18 MV links, 8 bits wide, with a SerDes that's moving at 25 gigabits per second. 25 gigabits per second on just one signal. There's 8 of them per link. There's 18 links on this one chip, and it's bidirectional. Altogether, it creates 7.2 terabits per second, or 900 gigabytes per second. So 900 gigabytes per second, by the way, of bandwidth, well, that's a lot of movies too. So 7.2 terabits per second, 900 gigabytes per second, goes through one switch. There are 12 switches. 12 switches. What that basically says is that every single GPU can communicate to every other single GPU at 20 times the bandwidth of PCI Express. Isn't that amazing? Every single GPU can talk to every other GPU. And every single GPU can talk to every single GPU in a non-blocking way. It's a fabric. It's not a network, it's a switch. It's a non-blocking fabric switch with a memory semantics, memory programming model that's exactly the same as what's inside our chip. And therefore, all the reads and all the writes and all the atomics just works across this. The bandwidth and the performance and the latency of this switch is incredibly low. It's incredibly low. Unlike a network, this is a switch, which means every single GPU can talk to the other GPUs with extremely low latency. You want to read, you want to synchronize a parameter, it takes no time. 300 gigabytes per second. And altogether, NVIDIA's largest graphics card. This is what it looks like. The largest graphics card. The largest graphics card the world has ever made. The largest graphics card the world's ever. 2 petaflops, 512 gigabytes. Most graphics cards in the world today, 2 or 3 gigabytes. 2 or 3 gigabytes. This is 512 gigabytes. 10,000 watts. 10,000 watts. Only. Only 10,000 watts. Only 10,000 watts. The amount of airflow is really quite amazing to cool it. And we designed this porous fabric in air intake in the front. It looks beautiful, but it's incredibly functional. Air comes traveling through it, flows through all of our chips. 10,000 watts of energy power is being thermal managed. 350 pounds. No human can lift it. No. 350 pounds. The first time I saw that, I was thinking, I could lift that. Didn't move. And I'm fairly strong. Upper body strength. And so, 350 pounds. What's inside it is 16 Tesla V132 gigs with 12 MV switches. And it's got this incredible what's called a playing card. It basically has 200 times. It has 200 times the bandwidth of the highest speed NIC on the planet. So imagine it's like 200 NICs of connecting the top to the bottom, connecting the top GPU tray to the bottom GPU tray. Each NIC, call it $1,000, $2,000. Call it $1,000. $200,000 of NICs would be required to connect the top to the bottom. It has that much bandwidth. It has that much bandwidth. If we were to use networking cards, well, we still have to connect multiple of these, and so we have 8 of the world's highest speed NICs from Mellanox to connect multiple of these systems together. It has the two fastest CPUs we can possibly buy, the Xeon Platinums. 30 terabytes of storage. 30 terabytes of storage on the system, because as you know, we're going to crunch through a lot of data really, really fast. So all together, ladies and gentlemen, it looks like this. This is the Nvidia DGX-2, the world's largest GPU, the world's largest add-in card, 2 petaflops, 512 gigabytes, 350 pounds, and just beautiful. This is... This is what an engineer finds beautiful, you guys. This is sexy. This is beautiful. This is unbelievable. Incredibly beautiful. And not to... Guys, did you guys notice the animation? NVIDIA's artists are so spectacular. This entire animation was shot with 112 shots. It's photographed. It's stop motion animation. This is not 3D. You know that we could do it in 3D, but we chose not to. Why? Because it's more fun. You guys want to see it again? Oh, stop motion animation, guys. Check it out. Guys, I love you guys. It's incredible. Tim Burton, you got nothing on us. Look at that. The world's largest GPU, 350 pounds. Well, let's see what it can do. 10 times faster than DGX-1. Does that even make any sense? 10 times faster than DGX-1. And so this is 6 months ago. This is literally 6 months ago. We showed these numbers. And the entire stack, look at the entire stack. There's so much software that's necessary to build this. This is a high-performance computer. It's a supercomputer designed for deep learning. And so look at this entire stack of software that was optimized. As a result, running PyTorch, the framework, and training FairSeq, the sequence-to-sequence model used for natural language, used for machine translation, literally took 15 days on a DGX-1, which was a world record at the time, and now it takes 1.5 days. Well, the amazing thing is, the researchers don't have 13 days left to sit around. The researchers are now using all kinds of techniques to use AI to create AIs. And so the number of experiments, the number of permutations, the exploration space of AI, sweeping through all the different configurations of architectures and the way to compose it, the number of layers, the training rates, sweeping through all of those hyperparameters and sweeping through all the different architectures at the same time is going to create just hundreds of experiments at one time. And so as a result, with bigger networks, more data, more experimentation, DGX-2 couldn't have come at a better time. And so it is 10 times in 6 months. Now, the thing that's really amazing is this. How much should we charge? I mean, look, it took hundreds of millions of dollars of engineering. It took hundreds of millions of dollars of engineering. This is the first unit, so this is, call it $250 million. And for just an incredible friend-to-friend price of $1.5 million, it seems like it doesn't even seem fair. It doesn't seem fair at all. Nah. Ladies and gentlemen, $399,000. You guys understand there are only 2 themes in this conference. That's right. The more you buy, the more you save. Okay? This front row's got it. We're going to keep working. All right? The more you buy, the more you save. And so $399,000 for the world's most advanced, most powerful computer. This is what it replaces. 300 dual CPU servers, easily for $3 million. Easily for $3 million. Easily for $3 million. But the important thing is 180,000 watts, 180 watts, in order to train FairSeek in 1.5 days. Well, it only takes one of these beautiful DGX-2, just one DGX-2, 10,000 watts, only 10,000 watts. 1/18 the power, 1/8 the cost. The more you buy, the more you save. It's incredible. You know, it's truly amazing how far we've come in just the last 5 years. We started talking about deep learning about 6 or 7 years ago, and at the time, the effectiveness wasn't anywhere near what it is today. 5 years later, since AlexNet, the progress that we've made is literally incredible. And I think it'd just be kind of fun just to do a report card, see what happened in the last 5 years. This is what it looks like. This is what Alex Krizhevsky trained AlexNet on. Two GTX 580s. Two GTX 580s. And it took him 6 days. But those were 6 worthwhile days because he became world famous, he won ImageNet, and kicked off the deep learning revolution. 5 years later, we could train it in 18 minutes. 5 years later, we could train it in 18 minutes. 500 times faster. 500 times faster. Isn't that amazing, guys? To be able to do a task 500 times faster in 5 years. To be able to do any task 500 times faster. Any task of great importance 500 times faster. Or to be able to do a task of great importance 500 times larger in the same time. This is some kind of a supercharged law that we're experiencing. Well, one of the things that made it possible, of course, is what I said earlier. This is an innovation that is not just about a chip. This is an innovation about the entire stack. Everything was touched. Thousands of engineers all over our company. From VLSI to process engineering to package engineering to circuit design, to architecture to chip design, system software, solvers and libraries and algorithms and systems all got involved. This is the effort. This is the work. This is the body of work of literally every single employee at Nvidia. We are all in on deep learning, and this is the result. And so over the next several years, it's going to be just utterly incredible because we're just picking up steam. This is some new type of computing. The amount of data is growing exponentially. There's evidence that with GPU computing, the computation is growing exponentially. And as a result, deep learning networks and deep learning models, AI models, are growing in capability and effectiveness at a double exponential. At a double exponential. More data, more computing, both on an exponential growth, compounding together into some kind of a double exponential for AI. That's one of the reasons why it's moving so fast. Really, really exciting times.